Hi, we're working on finding the discrete time Fourier transform of periodic signals. So I have this example, find the Fourier transform of the periodic impulse train. Here is the signal, the mathematical representation, and we want to plot the result. All right, the first question that you should ask yourself is the signal periodic? And that seems ridiculous in this video because we're told, but sometimes you're not told that it is periodic. So first of all, you should try to understand this signal. If you're like me, or when I was an undergraduate anyway, you might not be entirely comfortable with this signal in its current form. So the best way to get a handle of this thing is to pick a value of n is a parameter, and then try to plot it. So just for plotting purposes, let's pick n equals 4 or something. So we'll try to plot it versus n equals 4, and then start plugging in values of k, and because this is k, a sum from k equals minus infinity to infinity. So with n equals 4, when k equals 0, we have delta of n. Oh, delta of n. So that's this guy at the origin. Well, when k equals 1, we have delta of n minus 4. N minus 4. So that is 1, 2, 3. That's an impulse at n equals 4. This is n. Okay, now when k equals 2, delta of n minus 8. 5, 6, 7, 8. I think I get an idea of what's going on. Let's try some negative k's. How about when k is minus 1? Delta of n plus 4. Oh, that's an impulse shifted to the left by 4. I see what's going on. Right? So you can guess, I think now you can see that yes, this is periodic. And the period is shown here with n equals 4. The period is n, of course. Right? So yes, so the first question you ask yourselves is this periodic? If so, then I need this formula. The Fourier transform of a periodic signal is 2 pi times k equals minus infinity to infinity, a sum of the Fourier series coefficients of the multiplied by delta of omega minus k omega 0, right? That's what we need. And so we see that the period is n, and so the shown with n equals 4, and so the fundamental frequency is 2 pi over n, right? So we're just form fitting the Fourier transform, right? Here's the form of it. We just need to specify what the Fourier series coefficients are now. The AKs are the Fourier series coefficients. Okay, so I think we've done this before, but if not, let's find the Fourier series coefficients. Those were 1 over n times a summation n over 1 period of xn e to the minus j k omega 0 n were the Fourier series coefficients. So if you recall, I can take a sum over any one period. So let me just go from, as long as there are 4 consecutive samples in this case, shown with n equals 4. So how about there, 1, 2, 3, 4, to there, inclusive. Over that range, the only non-zero value of n is at 0, and where n is 1. So what happens here is that sifts out, this is the sifting property of the impulse. I have just an impulse in there that sifts out the value of e to the minus jk omega 0 n evaluated at n equals 0. So this is just 1 over n, and that's it, right? So the constant, I'll just point out that these are constant. They're all 1 over n. So now we've actually completely specified the Fourier transform. We've got the form-fitting equation here, and we've got the AKs are just 1 over n. They're constant. So really I can just say the Fourier transform. I can bring the 1 over n out because they do not depend on k. So I have 2 pi over n times a summation of k goes from minus infinity to infinity of these delta functions minus, and I'll write k and omega 0. Omega 0 is 2 pi over n, and that's it. that is the first part of it, I guess. Find the Fourier transform. There it is. Now, can you make sense of this result? At least enough sense to be able to plot it, right? And that's the key. So let's try. Let's try to plot it. I'll draw omega there. This will be x e to the j omega. Let's try to plot this guy. So this is a sum from k goes from minus infinity to infinity. So let's just try different values of k. K equals 0. This would be an impulse delta of omega scaled by 2 pi over n. So I know what an impulse looks like. That's this arrow thing at the origin scaled by 2 pi over n. Perfect. Okay, so let's plug in k equals 1. So added to that sum, added to our plot is 2 pi n times an impulse of omega minus 1 times 2 pi over n. So that's an impulse that has been shifted to the right by 2 pi over n. Okay, so there we go. Also scaled by 2 pi over n, right? And then the k equals 2 term would be shifted by twice 2 pi over n, so that would be over here. Right, so this would be 4 pi over n. All right, and we would just continue on like this. This is regularly spaced by 2 pi over n, 4 pi over n, 6 pi over n, so on. And then the k equals minus 1 term, you can work that out. Those are going to be impulses shifted to the left. So this would be minus 2 pi over n, then minus 4 pi over n, and so on. Okay, that's the Fourier transform. That's the answer. And I do want to point out that this is purely real, and it's purely real because xn is even. It's an even function. So this is foreshadowing some properties of the Fourier transform. So that it only takes one plot to draw a purely real transform. I also want to point out that this thing is periodic with period 2 pi. It repeats actually every 2 pi over n, so that when n is 4, we have 2 pi over 4, then 4 pi over 4, then 6 pi over 4, then 8 pi over 4. 8 pi over 4 is 2 pi. So yes, it repeats every 2 pi over 4, but it definitely repeats every 2 pi as well. And it needs to do that because the dtft is always periodic with period 2 pi.